Greetings. Welcome to another episode of the Insight Project. I haven't posted anything substantive since that video with 24 views talking about NATO was censored. But I thought, we'll post something on these silly little electronics experiments and just have fun with that. This is going to cover a lot of ground in a short period of time, and eventually I'm going to try and look again at two circuit nodes and talk about that. So let's get started without further ado. So right now what I'm doing is using an LCR meter to measure the inductance of this 10-pound coil of 14 gauge wire. Reads 35.45, and then you change the frequency 35.52, 0.51. So I've done this before and I put it in a spreadsheet, and what we have there is that the inductance is 35.46. You can measure the resistance with this, but it's better to measure it with a DVM, because if you measure with this, it gives you more places there, but look what happens when you change the frequency. So it's like, which is it? So I just go with what's on the digital voltmeter, which I think is bound to be more accurate. And so the resistance is 2.2. So what can we do then with that? So we know from that the tau time of the coil, L divided by R, is equal to that many seconds or that many milliseconds. Now let's suppose then that you had a 100 UF cap that you were discharging into that coil that we just measured just a moment. So as I was saying, if you have a 100 UF cap that you're discharging into that coil, then this is just a placeholder. I changed the capacitance from microfarads to farads. Then what is the cycle time? Now, what do I mean by the cycle time? The cap discharges, goes negative, then it comes back up a bit positive, then goes negative. So from wave crest to wave crest takes that many seconds, or 11.8 milliseconds. Therefore, what's the resonant frequency? The resonant frequency would be 1 over that, 1 over 2 pi times square root of LC. So the resonant frequency would be 84. However, that's wave crest to wave crest. So what's the point where it goes most negative? It would be half of that, or 5,915 microseconds. Now, that's when it went most negative. Now let's consider how long did it take for the cap to go from 10 to 0? In other words, how long did it take for the cap to discharge? So that's half again of this. So it's going to be a little less than 3,000. Since we know that, we can say that the coulombs of charge in this is equal to coulombs is equal to capacitance times voltage. So if you were at 10 volts and you had a capacitance of this, then this times this would give you the coulombs in the capacitor, and that number of coulombs discharges in, well, half of the time to go most negative, so 2,950 some odd microseconds. Now if you take 1 over that, that's how many discharges of that many coulombs you would get in a second. Okay, so we know that 1 amp equals 1 coulomb in 1 second. So from this we can calculate how many amps you're putting through your circuit if you're using a 50% duty cycle. In other words, well, really just how many amps are going through. So with the 100 UF at 10 volts, we're at 338 milliamps. And the part of the reason I do that is, for instance, the solid state relays that I'm enjoying using right now are called Comas AC37s. They're 500 milliamp 60 volt relays. And so sometimes previously, you know, I would go up to 30 volts. Poof! You know, you get the gray smoke. And you know, the joke I like to make is I elected a new pope. But you watch your circuit blow up. And you wouldn't think it. You know, you have just this little 100 UF cap, and you're at 30 volts. You know, oh, it can handle that. No, it can't. Now, if this were quicker, then you know, if you got down, instead of it being say 3 milliseconds, that it's discharging down like 1 millisecond, it can handle a pulse a little bit better. But you still, this is, you know, you wouldn't want to go over 10 volts with 100 UF cap, or you're in danger. Certainly you wouldn't want to go over 20, or you'll probably blow the thing up. So that's what that is just to keep that straight. And then the next thing, well, the next thing is I found a calculator online for skin effect depth, and they gave me the equation for it. And so that's what all these things are up here. You got your resistivity of copper, permeability of free space, relative permeability, and so on and so forth. So I can't remember the equation off the top of my head, but I plugged it in, and then I would plug it in and see what the calculator online gave, and it was given the same numbers. So now you can calculate the skin effect depth. So what is that getting at? Well, let's just go through this, and then I'll talk about what it's getting at later. So that's the skin effect depth. It's 7 millimeters. And then when you go faster with the 10 UF cap, it's down to 4 millimeters, and then down to 2.24 millimeters with 1 UF cap. Your wire diameter, however, with this, it's 14 gauge. That's an error. Let me see if this is an error too. Yeah, I forgot to update that from a previous page. So you can bring up a chart for wire gauge. Come on, scroll. Yeah, it's pretty cool. So here, if you have say 14 gauge wire, the diameter is actually 1.628. So I had that. I'll need to correct that. And that gives you the resistance per 1,000 feet. And, you know, how many amps. And this is, oh, come on, let me show it to you. Well, it didn't work too well, but this is what I'm getting at here, that 6,700 hertz would be the maximum frequency for 100% skin depth for solid conductor copper. So you know that if you go faster than 6,700 hertz, you're going to be increasing resistance because of skin effect with 14 gauge wire. What I don't know is if you're at say like 3,000 hertz, is there still an appreciable increase in resistance? Or perhaps you can get up to 10,000 hertz before it really becomes an issue. So that's sort of what I'm getting at. What did we say there? 1.62. 1.628. So now I put that 1.628 back in there. That's your wire thickness. And this is your skin effect depth. And then this is the wire diameter, the wire thickness, divided by the skin effect depth. And see, it's 0.22. So if this reached 1, the wire diameter, and it's getting close there with the 1 UF, what does that mean if it was 1? That means that in the center of your conductor, because of skin effect, and I'd have to do a separate video, perhaps I'll do a separate video on skin effect and proximity effect. Because of skin effect, the current carrying capacity is only equal to 1 over E, 1 over Euler's number. And I'm trying to remember off the top of my head, but I believe that means that the current carrying capacity in the center of your wire is now only, I want to say 63%. It might be like 62%. I'd have to look it up, but 1 over E. When the skin effect depth is equal to the wire diameter. Now, if you go further, it gets even worse until you could have, like 1% of the current going through the center of the wire, and it's just the resistance there is increased that much, and so all your current gets pushed out to the periphery of the wire. So you can see with some high frequency and thick wires, they don't even bother to put in the center of the wire. They just use hollow wires because the center won't carry any. But we're not there yet. We're starting to, you would start to wonder at 1 UF, are you getting there? And that brings up other problems, which I'll get to in a minute. But let's just talk more theory. I'm sure people are just sorry, I'm probably boring people, but if not, then let's just talk more theory. Leaving aside skin effect, let's pretend there is none, and for up here there's negligible skin effect. What determines then the Q factor, the quality factor of your LC tank circuit? And from what I can gather, the quality factor improves as a function of the resonant frequency divided by the tau time of the coil. And so really, I'm saying resonant frequency, but it's really, the discharge time. It's how fast the discharge. So, you hear people talking about, sharp transients. So it's how fast your discharge of your cap is divided by L over C. And you can put that in the spreadsheet. You see, well, for the 100 UF, it's 0.36, 0.11, 0.036. For a 1 UF, the lower this number gets, the better your Q factor. And I've been confirming that experimentally, except for I keep running into problems. I mentioned one there with the amps, but there are plenty of other problems that one runs into. Let's go over those quickly. One is what's the resistance in your system aside from the resistance in the wire. So here we have 2.2 ohms of resistance in the wire. I'm going to bring up now the spreadsheet for the Comas AC37 that we'll use to discharge this. The astonishing DigiKey. I have no relation to them, but I just want to make a video on them because they're just fantabulous. It's amazing. They've never gotten anything wrong. It's like the most obscure things. You can search for all kinds of ways. Anyways, so here's a Comas AC37. Not the spreadsheet, the data sheet. Let's just look at on-state resistance, drain to drain. Typical 0.75, max is 1.6. So you have about 1 ohm of resistance. Maybe it's 0.75, maybe it's even a little less, but maybe it's higher. So, we'll round it to 1 ohm. Now, we've got, going back to this spreadsheet, come on. We got 2.2 ohms in the wire, so we've almost added another third in the switch. So that's not great. However, I have found some other solid state relays where it's maybe the typical on-state resistance is like 0.2 or even like 0.1. So we can get rid of a lot of that, and that would improve the Q factor further. Another thing that kind of fooled me for a while, and I finally, Panasonic, you gotta love Panasonic too. They just do such a complete job. But this is, once I saw it, then I looked it up. It's also on the Comas thing. It says that the turn-on time is 0.2 milliseconds, so 200 milliseconds. However, when I was using this, I was noticing it could switch faster than that. And really, the turn-off time is also very important. But this is pretty good. It switches down to 200 microseconds and 0.05, but I actually, in practice, I was getting it switched down to like 80 microseconds. And so, what you want to look at, again, this should be a separate video, I'm just all over the place, is they're giving the value with the LED having a 10 microamp current. So here they give the graph of the turn-on time versus the LED forward current, and you can see that as it goes out to 50, you're not at 0.2, you're going a heck of a lot faster. And so what I benefited from is that, I don't really know what I'm doing, so I never stuck any resistors in there to get that down to 10 milliamps. And so the Arduino, I'll have to check the specs, but I think it's putting out like 30 or 40 milliamps. So you're down here. And what that means is that a lot of relays, solid state relays that I thought I couldn't use, I can use. And so now I can get this on state resistance even lower, down to like 0.2. Okay. So in other words, you want to, to be dramatic, you want a sharper transient. So you want to keep going down here, but eventually you're going to be faster than your solid state relay can switch. And so for that reason, I was initially putting some effort into, well, maybe I can opto-isolate a transistor. And I did that, but then it didn't really work well for this indication. It worked fine for like putting an LED on. And I also opto-isolated a MOSFET, and I didn't make a video on that, but that worked better. But what I'm starting to realize is I might run into all the same issues, and just the fact that I'm using opto-isolation means it might not end up being any faster than the 80 microsecond, 50 microseconds that I'm getting out of the solid state relays now. So it's like, do I really want to do that to myself? And then I also thought about, they have prepackaged opto-isolated gate drivers for MOSFETs, and I might want to go there, but it's sort of, do I need to? And this whole thing is like a wild goose chase. So it's like, do you want to do other wild goose chases? Really what I'm starting to think now is if I move away from the Arduino, just use the circuits that have been developed over the past 150 years for oscillators. The Colpitts oscillator, the Hartley oscillator, and however many others they have, and use that. And that's when I would need to get an oscilloscope for the oscillator circuits to see what the heck's going on. Okay, what the heck am I talking about? That eventually, as you're going smaller and smaller with cap, you're not going to be able to go fast enough with your switch, but that's much less of an issue than I realized. But there's still another issue, and that is, let's say you put your voltmeter on the 10 UF cap. It can just about get a reading. You go down to about 4.7 UF, it'll get a reading. You go down to 1 UF, it's discharged out through the 10 mega ohm resistor here before it can stabilize on any value. So it looks like it's doing worse, but I'm pretty sure it's actually doing better. So it's not a problem with any of your components, it's a problem with your measuring equipment, that it can't measure a 1 UF cap. So what do we do there? Well, what my thinking is that, we know per Ohm's law, Sorry, I had to. Ohm was a German physicist, and he came up with, the famous V equals IR. And so V equals IR, and I don't know because I can't measure it, but I can discern it, that there's a 10 mega ohm resistor that's kind of standard in this meter. So if you add another 10 mega ohms, since V equals IR, and R is doubled, all your readings will be halved. But I think that's the only problem. So what I did was I ordered 10 mega ohm resistors off of Amazon. And the thinking was, instead of having 10 mega ohms, I'll put 9 10 mega ohms resistors in series to make the resistance in total 100 mega ohms, all the readings will be 1/10 as high. And what do I care? So instead of 10 volts, now it reads 1 volt. It'll actually give you another digit of precision. And now you could measure this 1 UF cap the same as 10 UF. And I don't even know, maybe you could go out to like 900 mega ohms, be down to, instead of 10 volts, 0.1 volt. I don't know if you run into issues like with the circuitry in here. But as I said, I ordered the 10 mega ohm resistors off of Amazon, 10 of them, and they sent me 1 mega ohm resistors. So don't order electronic parts off of Amazon. That sucked. But order it from Discharging. I really like that company, and again, I'm not getting paid for anything, but they've never gotten anything wrong for me. It always shows up, and they have 10 mega ohm, they have 100 mega ohm resistors, and I'm pretty confident they'll actually send those out. But I did it just as a proof of concept, and it does work. And so you can just reduce the voltage reading, but then how much resistance you added, and so that allows you to measure 1 UF, and I'm hoping maybe down to like 0.22 UF, depending on how much, or even further. Then you can see how well that's doing. So let's just show some stuff now and have a little bit of fun. And this video is getting long, so we'll wrap it up. I'll try and wrap it up before a half hour. Then in the next video, we'll do a lot more. We'll get into all these other switches, and maybe then we can look at circuit nodes. But we'll just do a little bit with this, with Dish. And just sort of before we do that, I've already done this with a number of other coils, and so that's why I'm saying I kind of know what the changes are. The one I haven't mentioned yet is the change with voltage on the Q factor. And see, with those big caps, I'm not going past 10 volts because it blow things up. But so I've kind of been doing that with other caps, just gathering the data on it. So let's just do a little bit with the this 10-pound one we got sitting here. So now we have the circuit set up, and so this is very, very simple. You just have your bus lines here, and the negative is going through this switch into here, the positive is going in from that switch into here, and then those open, so now you just have a cap sitting there, and then you just discharge the cap through this one here, and there's your LC tank circuit. Really, probably the better way to do this, I'm starting to think, is just get rid of the whole cap thing and just set it up as a buck boost like John Bedini had, with the simplified schoolgirl and whatnot, because that gives you a constant voltage pulse. Whereas here, like if you're at 10 volts, it discharges in a set amount of time, but the average voltage will be 5 volts, and so you get a little bit more efficient use if you just get rid of this complexity. But what this allows you to see is it allows you to see more what's going on, and you do get away from the loss across the rectifying diode, the 0.8 volt or whatever it is voltage drop. So that's your circuit. You just charge up a cap and then discharge it. And we're not going to be doing anything with these today because there won't be time. And then here's the code for it. We don't even need the for loop, but we'll just do it once. And so we say pin 13, pin 11 high, that charges the cap, and then pin low, those low, and then pin 12 high and pin 12 low. I have these delays for a second. Let's go ahead and put those in just to be able to see that everything's working correctly. That'll just show us that thing's working. And then after it's done that, you delay for 2-3 seconds to get a reading. Actually, for the moment, I'm going to gray that one out. We'll put it back in later. So here I've just put the meter on the bus lines and seeing that we're at 10.01, good enough. So now I'm going to move the meter up to here. So when we do that, we put the meter there, we see the cap charging up and then discharging. and I can just about get a reading, but already it's struggling not to discharge out during that 1 second. Let's make that 3 seconds to see how quickly it discharges. So that's just showing how fast that cap leaks out through the meter. So you see, even with the 10 UF, it's becoming a little bit challenging to get a reading. You just got to look for that real high number there. It's actually 10.01 is what, but I wanted to settle at 9.99. So enough of that. So now let's get rid of those delays, and so we'll charge the cap, I don't know, 4 milliseconds and then a half millisecond for it to shut off. It's a little overkill. You can go faster, but it's only going through once, so who cares? Make sure the cap is fully charged and this is fully off. But those could probably be 1/5 for each of them. And then this is where you discharge it, and so we'll discharge it for on time number of microseconds, and then up here we'll set our on time. And what do we want to set it at? So we would go here and we say 10 UF. Well, it goes most negative at 1,871 microseconds. But let's first go through a full resonant cycle, 3,742 microseconds. 3742. Let's change this to 3742. And now we'll give it this 3 seconds here so we can get a reading on the meter and compile it. And turn everything back on. Okay, so what we're getting is 8.5 volts. So what you might be tempted to say is, well, you only gave it 3.7 milliseconds to discharge through all that wire, and so it hasn't had time to discharge. So now let's go twice as fast, and we're going to cut this number in half. 1871 now is what we're at. So now we hit compile. Negative 9.17. And see, it's hard to know exactly what it is, but it's around negative 9.16, maybe 9.17. So obviously it had time to discharge, and heck, it discharged all the way negative. So that's your, that's the measure of your Q factor there. 9.1. Look at that, 9.2. And so, just as an aside, with these breadboards, when it's not soldered, even moving from one pin to a pin where you feel maybe there's better connection, now it's going to 9.2 negative. So you can see the big effect that that resistance has. So if we cut this number in half again, that would be where the cap discharges to 0. Okay, I've learned something new, I think. So it was 1871. If you go down to 900, that's more than half, but it's still going a little bit negative. So there are two things. It could be something with components that's changing and is nonlinear, especially I'm thinking the timing of the switch, whether it's fast enough, or the other possibility is there's nonlinearity both in how this thing is charging, the tau time of the coil, and then you have the tau time of the cap, the RC constant. So there might be an interaction there, but it's close. So it's a little more than halved. It's just about going to 0. Now if we go to 800, now it better be. Yeah, see, now you're getting to the point where the cap just plain doesn't have time to discharge. And so we'll take it down to 100, which is about close to as fast as the switch can go. and so it's hardly discharging at all now. So now I've gone back to 900, and probably want to go a little bit faster, like 880 or something. But why do I bring up that timing? Because that's where you get the transformation of voltage if you have it set up as a buck boost. And why is that? So I don't know why I want to do this on a spreadsheet when I'm just doing it with my finger. But if you think about it, so the cap's discharging, and the cap doesn't have like some hidden negative voltage, it can continue to discharge. What's happening is the cap's discharging and the coil is charging. And so the cap discharges, it has a curve that it discharges with, the RC constant curve, and then the coil charges with its curve. And when the cap gets to zero, the amp strength in the coil is not going to increase because you're out of amps. So the amp turns would be, I believe, maximal when the cap gets to zero. And then it collapses. So what you want to do, well, first, I mean, if you just left the switch closed longer, like to the most negative point, so the coil charges to its maximal and then it discharges, the magnetic field is collapsing, and per Faraday's law of induction, then there's a displacement current generated, a radiant if you like. And where does that radiant go? It goes right back into the cap, except for it's inverting now because this is collapsing. So that's why the cap then goes negative. And then the coil goes to zero, the cap's now negative, and now the cap discharges again and charges this in the opposite direction, and the cap gets to zero, and then the coil starts discharging and now putting positive current, which is why we saw, initially when we went through the full cycle, like 8.8 volts, even though we were much further out, much slower. So let's just put that negative 9.2 in there. I think maybe we saw 9.21, but about negative 9.2. So it went from 10 to negative 9.2. So I mean, there's a number of things. Like, first of all, what might you do with that? What if you had a rotor and a pulse motor with bipolar commutation, and you discharge your cap and then you shut it off there when it's at negative 9.2, and then you only need to put in 0.8 volts and then pulse it again for, if it was north facing, then it comes in with the south facing. Now, I don't want to get, too overboard with that, because the magnet spinning past will have an impact on the coil, and I don't know what that is. You'd have to tease all that out, and if it's the same with a traditional setup as it is with like a zero force or a window motor setup, and it might not be. But what I can say is that, it gives you a nice starting point that you have over 90% of your charge. In this case, 92% of your charge, is back right where you want it for the next pulse. I don't know how well it would work in practice, but that's sort of something that would be interesting to do with a pulse motor. What are the other points that I want to cover here? Well, I guess, one thing sort of in the back of one's mind is, like, you went from 10 to negative 9.2. So that's a fairly undamped LC tank circuit. That's going to ring for a while. Could you ever get it to go from 10 to negative 10, then back to 10, and then negative 10, and just continue indefinitely in a self-sustaining oscillation? And I know, that's crazy talk. You're crazy, man. But let's do a search on Google, just real quick. So here we put in silicon carbide MOSFET self-sustaining oscillation. I guess these silicon carbide MOSFETs have come out, and I don't know, I don't follow this stuff that closely, but I'd say like over the past 5 years, and they have even lower on-state resistance than traditional MOSFETs. So if we search on that, this is what we see. So we You see all these recent articles in the engineering literature, analysis of the self-sustained oscillation of silicon carbide MOSFET, self-sustained oscillation half-bridge circuit, silicon carbide devices, self-sustained turn-off oscillation of silicon carbide MOSFETs, i.e. you turn it off and it doesn't turn off. Stability considerations for silicon carbide field effect, and on and on. And they're all very recent. Self-sustained circuit, silicon carbide. And a lot of them, I haven't read many of them, or I'm not sure if I'd understand them if I did. A lot of them are behind paywalls, but like here's one of the self-sustained oscillation silicon carbide MOSFETs. And there's that. It's a pretty high Q factor, I'd say. So it is quite interesting. I mean, the model I would have in my mind for an LC tank circuit like this, or I mean, with silicon carbide MOSFET, it's teeny tiny capacitance and a teeny bit of inductance and next to no resistance. But I mean, you visualize, or at least I visualize, an LC tank circuit like, say, a child on a swing. And it's like, well, you know, if you put in a magnetic air bearing or something, it's just going to swing a long time. But there'd always be some resistance. So, you know, what these articles are saying is that model of visualizing what's going on in an LC tank circuit is not necessarily correct, because there are self-sustained oscillations, you know, similar to the self-sustained oscillations of a photon in a transverse wave, where the electric field and the magnetic field just keep going boom, 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 boom in perpetuity. So bringing that back to here, I mean, that's a tiny little LC tank circuit. I mean, does that behavior happen on a macro scale? I don't know. I mean, you're 92% of the way there. So let's try and end this and see if we can do a little bit better. And just one more comment about, you know, like using this in a pulse motor with the bipolar commutation where you go back to negative 9.2. That's really the same thing as the Bedini schoolgirl circuit. But with the Bedini schoolgirl circuit, what you're doing is it's spinning and you're shooting this reverse voltage out to another cap, and then maybe you do a cap dump back to the source, and you recover 80% of the energy, 80% of the charge. However, if you have bipolar commutation, you know, why worry about all that? It'll shoot back on its own, and you'll get rid of the voltage drop across the diode. Now you got 92% back, so it's just a matter of what's going to happen with all the spinning magnets. So it's the same thing as the Bedini schoolgirl circuit, but just set up in a different way. Now we can't get a reading with the 1 UF cap, not until I get some resistors and see if that works. The other thing to do would be to try to go back maybe to have a high resistance data logging Arduino voltmeter, and I've seen they have like a $15 analog digital converter chip that is far more precise, so I may pick that up. But I have a 4.7, which I measured as 4.65, and let's put that in our spreadsheet. And now we see that's the most negative time, 1275. And you can also see how the amp draw, even though you're going faster, you don't go faster more than makes up for, you know, this is that much faster, but this is less than half. So your amp draw is going down as you're going smaller with the caps, even though you're going faster. So that's our amp draw. Let's put in a 4.65. Okay, so, you know, I'm also mentioning the resonant frequency over the tau time has an effect on this Q factor, your ending voltage there. And so we see that's improved, and of course it has, because the tau time stays constant and a resonant frequency is now faster. So let's see what it goes to. So this is about as small a cap as you can get a reading on without increasing the resistance. The other problem I'm having is this guy wants to pop out of his place. I'm holding him down with my thumb. So what is it? Is it 9.24 or is it 9.33? You see what I'm saying? It needs more resistance. 9.31. 9.32 I saw there. So I'll call it negative 9.32. So you can see went from negative 9.2 to negative 9.32. So it's a higher Q factor. And again, this is important. And so that's resonant frequency L over R. No, I'm sorry, resonant frequency 2 pi square root of LC over L divided by R. So if we get rid of the constant, the 2 pi, then you have square root of LC over LR. And I believe you could rearrange that. So you would say that what's important is R times the square root of LC divided by L. And so if you can make R smaller, that makes a big difference. If you make C smaller, it makes a difference, but a square root difference. And L, you have the L changing by the square root there, but in the denominator it's changing directly, so L being bigger helps by the square root as well. Okay, we can try one more thing. You know, we got plenty of room on the amps, so we can go to 20 volts. The problem is this is going to be even more of a problem at 20 volts because it's going to want to leak out faster at 20 volts than at 10. But let's see if we can see anything. So I put the meter on the bus lines. I hate that it likes to drift up. It's so hard to get it right. Stay. Okay, so we're at 20 volts. It might go to 1. I don't care. Well, this is not going to work. It just drains out too fast. I can kind of see 18.57 I saw once. But even that, 18.57 divided by 2 ends up, you know, 9, that would be 18.64. But the problem isn't that it's not improving, I'm fairly certain. The problem is that the meter can't catch it. So I am hoping that if I increase the resistance tenfold, I'll be able to catch that and see. So the very last thing I'm doing, and then I'll wrap this up. I've been talking for an hour. So I think we said it was 1276 was the calculated most negative, but you can kind of just set it at 1300, and then after each time decrement it by 5, so then, you know, 1295, 1290, because, you know, the other one was off by a little bit from the calculations, and I don't know if that's just, you know, the meter is measuring things wrong or exactly what's going on, but you might be able to find a place that's a little bit better. And so I just compiled it. This will be a little worse. The other one was a little faster, so it starts off a little worse. 2.9, I think we're looking for better than 3.2. There was a 3.2, and I saw there was a 3.3. I saw like a, I think a 3.6 or a 3.7. There we are at a 3.5. Yeah, there was a 3.6. But really, I need to increase the resistance here. But, you know, I'll take it, negative 9.36, and then it's going to start getting worse as it gets too fast. There was 3.7. Yep. So that's about as good as it'll do. Yeah, now it's starting to get worse. So instead of 9.32, we're up to 9.37. So let's wrap it up there. And what I need to do is go to Discharging and order some 10 mega ohm and maybe even 100 mega ohm resistors and see if I can improve this. If that doesn't work, I'll have to go back to using the Arduino as the data logging voltmeter and potentially buy that $15 chip, because the ADC analog digital converter chip isn't very precise on the standard Arduino. And while I'm at Discharging, I'll order maybe some other solid state relays and see if I can get this on state resistance from 700 ohms down to maybe like 200 ohms, which, you know, again, this thing has like 2.2 ohms of resistance, so that'll make a difference. I never got to circuit nodes on this, so that'll be the next, maybe the next video or a video soon. And that's just a way of getting a little excess energy without changing anything that's going on here by like similar to a center tap, but it's not really a center tap, but that's a whole nother video, so I'm not going to start on that now. In any event, that's what I'm doing. What have you been up to? So I hope people enjoyed it, and I do have fun with this, and so stay healthy, everyone. Bye-bye.